Okay. Okay, so these lectures are going to be on soft graviton theorem. Okay. So I'll begin by giving a general introduction to what is soft graviton theorem, because this is the first thing we should know. Okay. So let's suppose that you have an S matrix with the following external states, okay, with say n external states of finite momentum which I'll denote by P1 to Pn, and m external gravitons of small momentum, which I'll label as K1 to Km. So what soft graviton theorem is supposed to do that this gives a Taylor series expansion more precisely, it will be actually Lorentz series expansion, because it will also have some inverse parts, as we will see. So it's a series expansion of this amplitude of this S matrix in powers of the soft momenta, in powers of K1 to Km, and the reason that it's a theorem, okay, is that the coefficients of expansion are given in terms of the S matrix without the gravitons, without the soft gravitons. Now it's certainly not a priori clear that it can be done. Okay, that you have an S matrix which has certain finite energy particles and certain soft gravitons. Okay. We want to carry out a Taylor series expansion of the S matrix, which you can of course always do for any function. Okay. What is non-trivial about this Taylor series expansion is that the coefficients of expansion, okay, will be given in terms of the S matrix without the soft gravitons. But we will see that this works, okay, not to all orders. Okay, it works at the leading order, the subleading order, and the sub-subleading order. Okay, after that it breaks down. Okay, and we will try to understand the reason of this, why it breaks down and why there is a soft graviton theorem. Yes. Well, it's a ratio of the finite to soft. That's the scale, right? So it's a dimensionless ratio. So the expansion will be in powers of the ratio of ki's to pi's. Okay, other questions? That's right. So you'll think of k's as much less than p's and carry out an expansion in powers of k over p.
All the ratios are same.
We will take all the ratios of the same order, but there are also, see, this is what is called the simultaneous soft graviton theorem, but you can also take order, I mean, these limits one by one, right? That's the consecutive soft graviton theorem. Okay, so you can do various things, but we will be considering the simultaneous case. Well, that's in general the most complicated one.
So should it be graviton? It is true for any massless particle.
Well, soft theorem can be done for any massless particles, but for example, for the photon, there is a similar theorem. Okay, but there this expansion can be done for the leading and subleading order, but not beyond that. Okay. For the gravitons, the fact that the coefficients of expansion are given in terms of the S matrix without the soft gravitons is true for leading, subleading, and sub-subleading, and then beyond that it breaks down. Massless scalar, for Goldstones there are some soft theorem, but for generic massless scalars there may not be. No, not that the expansion breaks down. Okay. Expansion can be done, but the fact that the coefficients can be determined in terms of the S matrix without the soft graviton, that breaks down. That interpretation breaks down.
So for massless finite momentum, that contains strong interaction, weak interaction.
Everything, yeah, it doesn't matter. As you will see, the way we will analyze this doesn't matter what it is.
So for massless scalar, even at the leading order, the theorem may not work.
I think that the leading order you can find some kind of soft theorem. Okay. We'll see. I mean, once we get an understanding of why the soft theorem works, we'll see in the origin. So at most at the leading order, you may get something for massless scalar, but not beyond.
So the difference between sub and sub is spin 1 and spin 2. Is that the difference? Because
Well, we'll see. I mean, once you understand why the soft theorem works, then it will also become clear the difference between sub and sub-sub, right? Why for photons it works, it stops at sub, and for gravitons it stops at sub-sub.
when you say leading and subleading and so on, the power of k over
Yes, that's right.
not conservative.
No,
Where it was
all orders in perturbation theory. Yes,
and that is the power of the theorem.
exactly. Yeah. So you don't make any restriction of perturbation theory, and as Professor Mani said, that even when there are strong interactions going on in the finite energy sector, right, it will work even in that case. That's right. Yeah. So the soft photon theorem, exactly. External states, no. Finite energy states can be massive or massless. Gravitons are of course always massless, right? But for the external finite energy states, we will not make any assumption about whether they are massive or massless. They can be massive, yeah. So it works, for example, for string theory, where there are massive states in the external state. It will work there as well.
But can they, finite energy string, they can be also massless?
They can be also massless, yes. Okay, in particular, they can be gravitons themselves.
So, the Pi are just taking the scale of the process, right? With respect to which you call
soft, yes.
So at the end, shouldn't we be able to take that k tends to 0?
Yes, you can. That's the expansion, right? K over P. Yes.
Oh, so the expansion is in
Powers of K over P. Yeah. Okay.
S to the power 0 s and s square. Pi by Pi is s.
Yeah. Well, as you will see that the leading term actually contains inverse powers of K over P. Okay. So by leading, what I mean, the leading one is the maximum power of P over K, right, or the minimum power of K over P, and then from there on we will count subleading and sub-subleading. Yeah, so whether it's inverse power or two inverse powers depends on how many external soft gravitons there are, right? If there are only one external soft graviton, we will see that there is one inverse power, right? So there, you can determine the inverse power, the order k out of k to the 0, and then order k, right? Whereas for two external soft gravitons, the leading term goes as 1 over k square. Okay? So there it's 1 over k square, 1 over k, and 1 over k to the 0, right? That you can determine, and then beyond that, it's not given in terms of the S matrix without the soft graviton.
In the standard old way of doing the Lorentz theorem and so on, conserve vector current play a very important role.
Yeah. We'll not use that language, but physics will be the same. Okay, the gauge invariance will play an important role. right? But you will not use that language. Okay, so there are of course many explicit results on this. Okay, the first time the soft graviton theorem was discussed was by Weinberg in the mid 60s. Okay, so he discussed the leading soft graviton theorem. Since then, lot has been done. So, for example, there are some general results for subleading soft graviton theorem in 4 dimensions. Okay, that uses this BMS symmetry. Okay. Then there are many explicit calculations. Okay, there are results in specific theories in generic dimensions. Okay. But what we will be doing is to study soft graviton theorem as a completely general setting, okay, without putting any restriction on the dimension of space-time that we are working in, okay, or the theory that we are working in. Okay, so we will try to see in the most general setting what we can say about soft graviton theorem and to what extent it's valid. Yeah, dimension has to be, of course, the point is, okay, I'll discuss the infrared problems, right? So we'll see that in low dimensions, okay, the amplitude itself has infrared divergence. Okay, then it doesn't make sense to talk about a theorem, right? If the S matrix itself is ill-defined. Okay, so well, there are, okay, in 3 dimensions there are forget about gravitons. In 4 dimensions also there are infrared divergence, right? The amplitude itself is infrared divergent. So we'll have to deal with the infrared issues separately. Okay, so at tree level you can define this in any number of dimensions. Okay, once you start including loops, you have to be more careful about the infrared effects. Okay, those are the only ones which will be possible abstraction to the soft graviton theorem. Otherwise, the analysis will be completely general. Yes, they cancel not in the S matrix, they cancel in the cross section, right? So this is a statement about the S matrix, right? So you can in principle combine this into a inclusive cross section and then try to derive a corresponding soft theorem for that. Exactly. Okay, but we will be working at the level of S matrix, and so at the level of the S matrix, right, we can only work with soft theorem only when the S matrix is infrared, free from infrared divergence. So which means that in 4 dimension you have to restrict to either tree level or you restrict to dimension larger than 4. Right? In 5 and higher dimension there are no infrared divergences in the S matrix, so then it should be okay. Okay, so what we will be doing is to work with Feynman diagrams, okay, and we will be considering, okay, yeah,
You mentioned cross section.
yes,
I can write the expansion for S matrix and this set is not square. So I get a corresponding statement for the cross section. Sum over that.
yeah, that is divergent. Okay, inclusive cross sections you have to sum over soft emissions, right? Only then it becomes finite. See, if you just take the mod square of the S matrix, right? Yes, that is true. That will give a cross section.
So that will have an expansion.
That will be in 4 dimensions. That will be divergent.
No, I agree. You don't take the actual limit. You just keep the expansion as it is what you keep for S matrix. Right? S matrix you are going to derive the expansion.
Yeah, but the S matrix in 4 dimensions. So what I said is that in 4 dimension, right? If you just consider the S matrix, at tree level it's perfectly fine, okay? And the soft theorem that we'll be discussing will hold for the tree level S matrix. Okay? But if you consider the quantum corrected S matrix in 4 dimension, that is infrared divergent. That's already divergent, right? So it's not clear what is the theorem means for a divergent quantity, right? So that's the reason why we, if we want to consider soft theorem, we will be restricting either to tree level, in which case you can work in 4 dimensions as well. If you want to go to loops, then you go to higher dimension. Okay, so we will be considering Feynman diagrams, okay, but because we also want to include complicated interactions, okay, which may involve, for example, QCD interactions, for which we do not know what the Feynman, the Feynman diagrams really don't make much sense. Okay. We will be using the language of one particle irreducible effective action. Okay. So the elementary fields, okay, which will be the external particles of the S matrix, okay, could even be composite particles. Okay, it doesn't matter. Okay, you think of working with one particle irreducible effective action, okay, where the elementary fields could be composite. Okay, it takes into account all the possible strong interaction effects and so on. Okay, and draw the Feynman diagrams with that one particle irreducible effective action. Okay. So keeping this in mind, we will divide the Feynman diagrams that contribute to a graviton amplitude into two classes. Okay. And let me from now on be more specific, okay, and discuss the case of single soft graviton. Okay, later on we will see how to generalize this to multiple soft graviton case, but right now we consider only single soft graviton. Okay. And here we divide the Feynman diagrams into two classes. So let me label these. This carries momentum pi. Okay, but in this we will be missing the So what is special about this diagram? So let me take these gammas here are full amputated Green's function, not even 1 pi. Okay, these are the full amputated Green's function. So if you use the language of 1 pi effective action, then these gammas will involve tree level amplitudes computed using 1 pi effective vortices. Okay, because 1 pi vortices have the property that when you calculate the tree level amplitudes involving the 1 pi vortices, they give the full quantum corrected amplitude. Okay, because all the loops are included in the definition of the 1 pi vortex. Okay. These gammas involve the full amplitude, okay, amputated amplitude, which means that full tree level amplitude using the 1 pi vortices. Epsilon I, sorry, this is pi, no, not pi, sorry, epsilon I pi. Okay. So the epsilon I and pi are the polarization and momentum of the external states. So I'll be more specific about what the polarization means. Okay, something which labels other quantum numbers, anything other than momentum. Okay. Here, this is a 3-point function. Okay. One soft graviton. So this is the notation for a soft graviton. Epsilon is the polarization of the soft graviton. K is the momentum of the soft graviton. Okay. These are the finite energy particles. And these are also the finite energy particles. Okay. So this class of diagrams means that this corresponds to diagrams where the external soft graviton gets attached to an external line, okay, through a complicated vortex. Okay. This is of course 1 pi by construction, right? I mean the only 3-point contribution of vortex is the 1 pi vortex. Okay. This one gamma, okay, is a general amplitude. So this is one class of diagrams. The other class of diagrams is anything that doesn't have this. So let me draw this diagram and then we will be discussing. So gamma tilde excludes diagrams where the soft graviton attaches to an external line. Okay. So let's try to be clear. This is, so we have divided the set of all Feynman diagrams into two classes. Okay. One class where the soft graviton gets attached to an external line, okay, by some 1pi vortex. That's this class of diagrams. Okay. And then the rest, okay, where the soft graviton attaches to something inside, okay, not to an external line. So for example, in a 4-point scattering, let me give a simple example. In for n equal to 4, well, I'm labeling it by small n. Okay, let me put them capital N because I had used capital N as the number of finite energy particles, right? So epsilon capital N. So for n equal to 4, a diagram like this, some vortex, we don't care. Okay. This one will belong to gamma tilde. Okay, because soft graviton is not attached to an external line, it's attached to an internal line, or it could also have attached to a vortex. Okay. So these are examples of graphs that contribute to gamma tilde. Okay. On the other hand, if the soft graviton attaches here, it's part of these diagrams. Is this revision clear? Okay. So the point is that all diagrams can be divided into either this class or that class. Okay. Because it's a binary possibility, right? The soft graviton, it either attaches to an external line in the diagram or it attaches to some internal vortex or internal line. Okay. And those are the two classes of diagrams I have drawn. Yes.
So the first part, which is the 3-point function.
Yes.
If you have taken gamma to be 1pi.
Well, it has to be 1pi because what else can you draw, right?
No, it can be elementary vortex also.
Yeah, but that's part of 1pi, right? 1pi contains the elementary vortex but also composite vortices.
My question is, why do you not focus on elementary vortex and look at the more line? Because that line can be taken. It has to attach to some line.
Yes, it has to attach to some line.
What generality are you getting by doing this?
Oh, because I want to include, for example, suppose you have a diagram like this, right? This diagram I want to include in this class instead of including other category, right? We'll see why. Okay, but that is a division. Okay, first it should be clear that we are dividing the diagrams in these two classes. Okay? One of this kind, which includes that diagram in particular.
So this allows the middle line to be different from the external line.
Yes, this allows the middle line to be different from the external line, exactly. Okay, so those are all included in this. Is this clear? Exactly. So that happens in this diagram but not in that diagram. Okay, so let's see the difference between the contribution from these two diagrams. So in the first diagram, let's look at the this propagator, right? So this one carries momentum pi plus k, right? Or minus pi plus k if we count it this way. So this has a denominator factor which is 1 over pi plus k square plus m square. Of course, there can be numerator factors also, which we don't care right now. It has a denominator factor like this, which can be written as 1 over, it's a pi dot, so pi square is mi, so this, let me write pi square plus 2 pi dot k plus k square plus m square. K square is 0 because the graviton is on shell, okay, and pi square is minus m square, sorry, pi square plus mi square is 0, okay, so mi is the mass of the ith particle. Pardon? Well, I am using the mostly plus signature, right, which I don't know, I mean whether it's opposite or the same, I mean it's pi square is minus p0 square plus p vector square. No. Yes, I am putting plus, exactly. Yeah. Okay, so using this, right, this can be written as 1 over 2 pi dot k plus m square minus mi square. Okay. And if we consider, so this means that this goes as 1 over 2 pi dot k if mi square, if m square is mi square. Okay. So that possibility always exists, that what this internal line need not be the same as the external line, but it can be. Okay. And if it is the same as the external line, okay, then this goes as 1 over 2 pi dot k. Okay. So this has a pole. Okay. This is the inverse part that I was talking about. Okay, it goes as 1 over k. Okay. And this, in this case, is the leading contribution. For one soft graviton, the leading contribution goes as 1 over k, and that's the origin of this 1 over k. Okay. So this propagator gives a 1 over 2 pi dot k. Yeah, then it's of order 1. Okay. But when you take this class of diagrams, okay, there is always some contribution where the internal line is the same as the external line. Okay. That contribution goes as 1 over pi dot k. Okay. So that's the leading contribution. Okay. So what we conclude then is that this class of diagrams gives leading plus, of course, subleading, subleading and so on, right. Once you have the leading contribution, then there are corrections which gives the subleading and then subleading and so on. But its contribution starts at the leading order. Yes. Well, if it does contribute a k, right, then the leading contribution will be 0. But we are allowing for the possibility that this can give leading contribution, right. If it contributes k, we will see that this will actually go down back to k to the 0, right. But we will see later that it doesn't contribute k, right. The leading contribution of vortex will determine, and it will be non-zero result. Is this clear? Okay, so this says that this has this diagram can possibly give a leading contribution of order 1 over k. This diagram, on the other hand, doesn't have such propagators, right, because this soft graviton is attaching to an internal line. Okay. So this starts contributing at subleading order. Starts at subleading order. Are there questions? Yes, true. The point is that I am just saying here that there is a possibility that, so let's define the leading contribution as 1 over k. Okay. Then there is a possibility that this begins contributing at leading order. It could be that the coefficient is 0, okay, but you have to allow for the fact that this can contribute at leading order, because you have not shown that this vortex has a factor of k. Okay. But this vortex, okay, does not start at leading order, right? It doesn't have a 1 over k.
Okay, this is leading with some of the coefficient that is sublime.
Exactly.
But it may happen that this is k to the positive, that is also contributing
True.
to the positive.
True. Let's, I agree. Let's define the leading as 1 over k. It may happen that the leading contribution is 0. Okay. Then you have to rethink about what you mean by leading, right? But let's naively, this gives 1 over k. So let's define the leading as 1 over k, right? If it becomes 0, then you'll worry about it later. Okay, we'll see that it will not be 0. Okay. So let's begin with that possibility. Okay. So we define the leading to be 1 over k, in which case this gives leading contribution, and subleading and sub-subleading. That starts at subleading, and then it can give sub-subleading and higher order contributions.
You have not talked about the smallness of
About the?
smallness of.
Well, I have in some sense talked about smallness of k, because in declaring that this is leading, right, I am assuming that this thing is small, right. See, because it has 1 over pi dot k, right, it's large, right, it's large because it has 1 over pi dot k, and based on that I declare that that is leading. Okay, so at that stage you have used the smallness of k. Okay, are there other questions? Okay, so now
Internal line, you mass for the internal line and
m square. So if that internal line happens to be the same as the external line, then you get this contribution. Okay. So this includes that contribution also, right? Here you are summing over all possible internal lines, right? What I mean by this diagram is that you are summing over all possible internal lines. Okay. Yeah, so at least in one case it will have m equal to mi. Okay, so we have to compute these Feynman diagrams. Okay, that's then we can hope to get something about know something about soft theorem. But the problem, of course, is that we don't have the Feynman rules. Okay, because we don't have an action, right? We don't start with a specific theory. Okay. So the question that we have to now try to address is how to compute Feynman diagrams, okay, when you don't know the action. Okay, and this is what we will try to study. We will see that we will assume a generic form of the answers and gauge invariance to fix the Feynman rules. Okay, so here will be the strategy for the calculation. So we don't know the action, but we assume that there is some action. Okay, of course the theory should have an action, 1 pi effective action. So that's the first assumption, that let's consider the gauge invariant 1 pi effective action. Gauge invariant in this case also means general coordinate invariant. Okay, so now given an action, how do we derive Feynman rules? We expand in powers of fields, right, including the metric. Okay. So we expand in powers of fields to determine the vortices. Okay. And for the metric, we will write g mu nu as eta mu nu plus 2 h mu nu, the standard expansion, where h mu nu is a fluctuating field, and expand out in powers of the h mu nu. Okay. So that's the second step. So we expand the action in powers of all fields. fields, including the metric. Yes, so we are always talking in terms of effective action. Okay, so once you have the effective action, you only do tree-level calculation with that. No, that's the point. We will assume that there is some effective action, right? That even in QCD, right? You integrate out. I mean, you do all your quantum calculations, and you can write down some effective action of protons and pions coupled to gravity, right? So you assume that there is such some effective action of that kind, which will have lots of higher derivative terms to arbitrary order. We don't care, okay? Some effective action, and that's what is our starting point. And the only thing about the effective action is that if we take that effective action and do tree-level scattering, we will get the scattering amplitude.
How do you know that effective action in the forward?
Because we assume that the theory is general coordinate invariant. That's the input. Okay, because we will be proving the soft graviton theorem in a theory which has general coordinate invariance, and we will assume that all the anomalies etc. are cancelled so that the general coordinate invariance is not broken by quantum effects.
Can go to arbitrarily high dimension of the operator.
Yes, it can. So we will not assume anything about where it truncates. Pardon? We are expanding on the flat space. So we will assume that a flat space is a solution to the equations of motion that are derived from the effective action. Right? Otherwise, of course, it doesn't make sense to ask about S matrix at all, right? So flat space better be a solution, right? So if, for example, the loop corrections generate a cosmological constant, then there is no point in asking this question about S matrix. Okay? So we assume that a flat space is a solution, and we expand on the flat space matrix. Has G mu nu equal to eta mu nu is a classical solution, and other fields set to appropriate expectation values, right? And we assume that this background is Lorentz invariant, right? So only scalars can take expectation values. G mu nu is eta mu nu. Is this okay? True vacuum, yes. And we assume that true vacuum is Minkowski, right? Otherwise, S matrix doesn't make sense. True vacuum, yes, in all other fields, right? That it has it's a Minkowski space is a solution to the full quantum corrected effective action.
Sorry, so there is a non-zero lambda. We know that it breaks down, or
well, if there is a non-zero lambda, then the S matrix doesn't make sense, right? You have to ask a different kind of questions. So this soft theorem is a statement about the S matrix. And that makes sense only in flat space.
But if there is a small lambda, we can take it as a perturbation around the flat, and then maybe even some non-zero lambda.
Okay, yeah, then you think of it as a perturbation, you just then it's as good as saying that the metric is flat, right? And you ignore the effect of lambda, right? Of course, in our universe, right, we can talk about S matrix, right? And you just ignore lambda in that calculation. So that you can certainly do, right?
So because we are going to take arbitrarily small momentum of the graviton,
it cannot be so. Okay, so the point is in our universe, right, the soft graviton theorem obviously will break down when the momentum is of the order of 1 over the size of the cosmological horizon, right? Because in de Sitter space the S matrix itself breaks down. So the momentum has to be small compared to the other finite energy particles, but still large compared to the scale that is set by the cosmological constant. Yes, so this whole argument is about S matrix, and S matrix is defined for asymptotically flat space-time, right? So we'll assume that asymptotically flat space-time is a solution to the equations of motion. Is this okay? No, they can be gravitons also.
No, other than gravitons, like photons.
Yes, that's perfectly fine. Yeah, that's also fine. Right? So we are at present we are considering one soft graviton, arbitrary number of finite energy external states, massless or massive doesn't matter. Meaning the theorem can be even stated for asymptotically flat spacetime, because S matrix, right, is defined only for asymptotically flat spacetime. Oh no, H mu is a fluctuating quantum field, so you are not allowing H to have a vacuum expansion value, right? So H mu will be describing the gravitons that will scatter. The solution, the classical solution about which you are expanding, is flat spacetime. Yes, so G bar mu nu is eta mu nu. Yes, it's eta mu nu, exactly. So G bar mu nu is eta mu nu. Well, it's not just asymptotically flat, it's flat spacetime. S matrix, because the vacuum about which you are doing the expansion, right, has to be transition invariant. Yes. Yes, that's right. No, it's applicable to flat space-time background. Forget about asymptotic, yeah. Flat space-time background. No, yeah. Flat space-time background. Okay, that's why we are applying S matrix. Notion of S matrix makes sense. Yes, that's right. So the metric has to be, the background metric has to be eta mu nu. Okay, because otherwise what is the S matrix doesn't make sense, right? Yeah, but the point is, imagine that you have a torus, right? That also has flat metric, right? But the notion of S matrix is not clear on a torus. Yeah, exactly. Yeah. Okay, so now third step. So this part is quite standard, right? I mean, this is what we would do in a normal quantum theory, right? We take the one pair effective action, then we expand in parts of all the fields, right? If you want to calculate graviton scattering, that's what you do. You write G mu nu as eta mu nu plus H mu nu and expand. Yes. Oh, let's forget about asymptotical flat. We are going to work in flat space time. Yeah, flat space time. Okay, where S matrix. Okay, but let's do flat space time for now. Okay, then we will worry about it. When transition invariance is broken, then there are additional complications which will not worry about now. Okay, so the third step is to add. So here is one important step: add manifestly Lorentz invariant gauge fixing term. Okay, so we choose our gauge fixing term so that it, of course, it has to break general coordinate invariance, right? If you are gauge fixing, it better break general coordinate invariance. But we will choose the gauge fixing terms to be manifestly Lorentz invariant. Okay, and I should perhaps set Poincare invariant, because you also don't want to break transition invariance. Okay, so the Poincare symmetry is preserved by the gauge fixing term. So normally, once you have carried out up to step 3, you can start calculating S matrix, right? Now your propagator is well defined, you can start drawing Feynman diagrams and calculate S matrix. Okay. But it is at this stage that our strategy for doing the calculation differs from the standard procedure. Okay. So the way it will differ from the standard procedure, okay, is that we will use this action, to derive Feynman rules for finite energy particles but not soft gravitons. Okay, so this is the important step. So this action now can be used to derive vortices. Okay. If you wanted, you could also use this action to derive vortices for soft gravitons, right? Because this includes all gravitons. Yes. No. So finite energy is in the center of mass frame, say, center of momentum frame. You can of course take this whole process and boost it, right? Then of course all the soft gravitons will also have the finite energy, right? So let's fix it in the center of mass frame, right, where soft makes sense. Okay, you can of course give a more Lorentz invariant notion of what you mean by soft, right? It's a pi dot k over pi dot pj should be small. Okay, but if you fix in the center of momentum frame, then this problem doesn't arise. Oh, if there is infrared divergence, then what? None of these 4 steps break down. What happens is that the vortices of the 1 pair effective action, okay, could have inverse parts of the soft momentum because of the infrared divergence, right? And we will assume that if there are inverse parts of soft momentum, they always come from the propagator and not from the vortices. Okay. That's why the infrared divergence properties have to be under control. Okay. So our analysis will assume that the 1 pi vortices do not have inverse parts of soft momentum. Only from the propagator, exactly. Okay. For elementary vortices, this is manifestly true, right? Elementary vortices have derivatives which gives positive parts of momentum, but never parts of momentum in the denominator, right? We'll assume that the 1 pi vortices also don't give inverse parts of soft momentum. Right? These can break down if there are infrared issues. Yeah, but the infrared divergent contributions will give that kind of interaction. Right? That's why we have to separately make sure that the infrared issues are under control.
Sorry, is it easy to give an example for 3, or what kind of gauge fixing terms on that?
The analog of the Lorentz gauge, del mu h mu nu whole square, for example. Okay, that is a gauge condition which is Lorentz covariant, right? Or Didondar gauge, which you take del mu h mu nu minus h, the trace of h whole square, right? So those kinds of gauge conditions are okay.
So you will explicitly need that?
No, we will only use the fact that it's Lorentz invariant.
But you will need that the gauge is fixed.
Yes, yes. Because otherwise you cannot derive Feynman rules. Right? Propagator is not well defined if the gauge is not fixed. Okay, so we'll assume that the gauge is fixed. Is this okay? Okay. So as I said, let me emphasize for again that this action that we arrive at this stage, we are going to use to derive the vortices and the propagators for finite energy particles, but not soft particles. Okay. In fact, for one soft graviton, we don't really need the soft propagator ever. You can see that for the soft particle, we only need the 1 pi vortex. Okay, so now step 5 is how to calculate the soft graviton coupling. So to calculate coupling of soft graviton, okay, which are denoted by a separate symbol S mu nu, okay, which is to be distinguished from the metric fluctuations that occur here, okay, the h mu nu, which describe finite energy gravitons. Okay. So to calculate the coupling of S mu nu, we covariantize the action in step 4. So this is the key step where our analysis, that our strategy differs from the usual way of deriving coupling. Okay. That we have already gauge fixed. Okay. We can derive the Feynman rules from there. Okay. But we pretend that we have gauge fixed only the hard gravitons, only the finite energy gravitons. Okay. That for the soft gravitons we don't even include what they are here. Okay. We take this action, okay, and then we covariantize again with respect to the soft graviton field. Okay. Given Lorentz invariant action, we can covariantize, right? We replace eta mu nu by the metric G mu nu. Okay. That G mu nu in this case will be eta mu nu plus 2s mu nu.
Sorry, I'm now a bit confused. So the
Yes.
field is the same h mu nu when the momentum goes to 0 is the soft.
Yes.
So what do you mean when you say
We are thinking of h mu nu as describing only the hard gravitons. Okay. And for the soft gravitons, we introduce a new set of fields whose coupling we determine differently.
so h mu nu is only the hard
Hard part, yes.
But when that momentum goes to 0, what happens to
Well, it will become part of S mu nu, but there is a clear separation, right? Because you are doing tree-level scattering with this, right? So you don't never have to worry about loop momentum, which could run over all possible values, right? In any tree graph, right, every internal momentum is either hard or soft, right? So there is a clear distinction between which particles are hard and which particles are soft. We use different Feynman rules for the soft particles than for the H mu nus.
but for the external leg?
For H mu nu, for external finite energy legs we use these. Okay. For external soft legs, we use this procedure. Yes.
I have originally you wrote it in determining pattern.
Yes.
Now you are going to write it in this background, it should be the same.
Exactly. That's right. Okay. So it's that you have a choice of expanding the action in two steps, right? That you expand the original action in the background of eta mu nu plus s mu nu, okay, and the coefficient of we write the action as eta mu nu plus s mu nu plus h mu nu, right? Stated that way, it's clear that the final thing depends only on the combination s mu nu plus h mu nu, right? So you can transfer back and forth between s and h, okay? But we do it in two steps. We first write eta mu nu plus h mu nu and then covariantize again, right? Which is equivalent to having written the original metric as eta mu nu plus h mu nu plus s mu nu. Okay? The only difference, okay, is that this Lorentz invariant gauge fixing term that we choose for the h mu nus, right, they are now covariantized with respect to s mu nu. Okay? Which means that the gauge fixing term for the hard part, okay, we are choosing in such a way that it's already covariant with that doesn't break the soft gauge invariance. It's a choice of particular gauge for the hard part. Right? That's the only physical input. Yeah, that imagine that we forget, if we did this before this step, right, before the gauge fixing term, then what we are doing is equivalent to writing the original metric as eta mu nu plus 2s mu nu plus 2h mu nu, right? We are thinking of the s as a soft particle, soft graviton, h as a hard graviton, but of course it's clear that the final result depends on only s plus h, so you can transfer back and forth. Okay? So you could either do this expansion first in terms of h mu nu and then covariant with respect to s mu nu, you will get the same result. Okay? But adding this step, right, here you have added, for example, the del mu h mu nu whole square, okay? But what you are saying now is that this, what you have added is not del mu h mu nu whole square, but it's d mu h mu nu whole square, where this d is a covariant derivative with respect to this metric.
That's the procedure of covariantization.
Exactly. That's the procedure of covariantization with respect to that. So that's a physical input.
Plus curvature terms is also.
Yes. So I'm coming to curvature terms, right? But this is one step that you have to covariantize with respect to S mu. Plus for the gauge fixing term. See, for the original action, right? You can write it as you can do it in 2 steps or 1 step. Okay. For the gauge fixing term, right? Here you are necessarily breaking. Well, it is done for everything else, but for everything else, it doesn't matter whether you have did it in 2 steps or 1 step, right? You could have at this stage written h mu nu equal to h mu nu, replace h mu nu by h mu nu plus s mu nu, and you will get that answer that you will get from there. Okay. But for the gauge fixing term, right? As I said, it doesn't make sense. You cannot choose the gauge fixing term to be general coordinate invariant, right? Clearly. But what you can do is that you can choose the gauge fixing term for the hard part as general coordinate invariant under the soft gauge transformation.
Right. So if I were to just consider theta mu plus 2 s mu as my background and then do the expansion, I will get everything in one stroke.
Yes, that's it. You will get everything to one stroke, provided also the gauge fixing term you now choose as d mu h mu nu whole square.
Right. So I will use the covariant derivative
With respect to s mu nu, exactly. Then everything is fine.
So in a spirit, if I had chosen the fixing term to be s plus h, if I had taken that, this is a different fixing term.
Yes, that's right. So the gauge fixing term can never be.
This is not true for the other part.
Yeah. So the gauge fixing term can never be fully general coordinate invariant, right? But you can ensure that the gauge fixing term for the hard part. Here we only need the hard propagator for these diagrams, right? You can ensure that the gauge fixing part for the hard part is covariant with respect to soft gauge transformation.
It is another Lorentz invariant term.
It's another Lorentz invariant term, exactly.
So that will introduce interaction between hard graviton and soft.
Yes, exactly. But that's a gauge artifact. So individual Feynman diagrams, of course, will be different, right? From these Feynman rules or from the original Feynman rules. But the S matrix will not change.
But it fixes only hard part for the propagator.
Yeah, soft propagators you don't need anyway, right? For this diagram, as you saw, that none of these diagrams has a soft particle in the internal state, right? So you don't have to fix the soft gauge invariance.
So there is implicitly some function which takes, so if I take S mu nu and increase its momentum, implicitly there is some function which takes everything to 0 as well as flatness, so that otherwise there will be some double counting, right? I mean, if I include hard momentum in S mu nu.
Yeah, so that the point is that because you are using 1pi action, see if you are thinking of things propagating in the loop, right, then you will worry that whether there can be double counting, right? But in a tree diagram, right, in a given process, every line you can identify either as hard or soft, right? Its momentum is not varying, right? It's fixed by all the external lines. So there is no confusion about double counting, right? In fact, in this diagram, all internal propagators are hard, right? S appears only as an external leg. Okay. So there is no possibility of any double counting.
But in the external leg, if I increase the momentum of the
Yes, yes.
then what happens? Something should.
Well, nothing will go wrong, but we will see that this procedure breaks down. I'll explain why. Okay. That this, I mean, what you are doing, right? This will not give any, simplification. Okay, if S momentum was hard. Okay, I'll just explain in a minute why that is the case. No, because that's why we take the 1pi effective action, then we covariantize, right? Because once things start propagating in the loop, then you have to worry about whether the splitting between hard and soft is all right or not. Okay, so this covariantization is being done at the level of the 1pi effective action. Okay, so this means what? That first we replace eta mu nu by eta mu nu plus 2s mu nu, and then replace all derivatives by covariant derivatives, all derivatives by covariant derivatives. With respect to the soft metric, with respect to Why? Oh, that's just a matter of convention, right? Because ultimately we will be working with Feuerbein's where you have to take the square root, right? So there it will be S mu nu, but it's just a matter of convention. Normally when you expand the Einstein action, I mean you take G mu nu as eta mu nu plus 2 kappa H mu nu, right, in the standard normalization. So that's the factor of 2. Kappa I am setting equal to 1. Okay, but one important point is that this procedure, this will miss terms involving Riemann tensor of S mu nu. So if you take this metric eta mu nu plus 2 S mu nu, you can compute a Riemann tensor with it, right? That's completely covariant. Okay. So when you say covariantize, okay, you always have the possibility of adding terms to the action which involves coupling of the corresponding Riemann tensor. Okay. So the action that we get here could differ from what we would have gotten if we had stopped at this stage and thought of S mu nu as part of this, okay, by a Riemann tensor of S mu nu. Even if the original action didn't have R mu nu coupling, okay, it could involve extra powers of extra factors of Riemann tensor.
Yeah, that's what I mean. If there is no curvature coupling in the original one,
Yes.
then you won't generate it just by.
No, you could, because the point is you have the ordinary derivatives, no? The ordinary derivatives you are replacing by covariant derivatives. Okay, commutator of covariant derivatives has Riemann tensor, right? So when you say, if you suppose you have del mu, okay, you generalize to d mu d nu. Now if you generalize to d mu d nu or d nu d mu, nobody tells you, right? So that differs by Riemann tensor, right? So those terms you will miss, right? You cannot fix it by this procedure. See, suppose you have del nu of some field, okay, you covariantize. When you covariantize, you could write either d nu of the field or d nu d mu of the field, right? These two are not the same, right? They differ by Riemann tensor, right? So when I say that you take the original action and covariantize, I could have covariantized either by writing it as d nu or as d nu, right? Both of them cannot be correct, right? Some linear combination may be correct, okay? But we don't know what linear combination is correct, right? So for that reason, we know that the terms involving Riemann tensor we are missing, right? Because adding terms involving Riemann tensor doesn't destroy general coordinate invariance with respect to soft gauge transformation, and you can always add such terms, and they are in general present in the action. Well, the original action doesn't have this ambiguity, right? This action, if you had stopped here,
If you have done it in one stroke instead of 2 steps,
yes,
you will not get the problem.
no, then you would not have the problem, because then that action is unique, right? You would get some answer. Because you are doing it in 2 strokes, right? Here, in the process of covariantization, right, you are missing out that knowledge of what the term involving Riemann tensor would be.
It's like the non-minimal terms which cannot see in flat space action.
Exactly, the non-minimal terms which you cannot see in the flat space action, right? When you covariantize a flat space action. Okay? So those are ambiguous, right? But a Riemann tensor of S mu nu has 2 derivatives of S mu nu, right? Those are 2 powers of soft momentum. Okay? So a presence of a term which involves Riemann tensor of this S mu nu, okay, could affect our result at sub-subleading order, right? Because it has 2 powers of soft momentum. Is that point clear? Okay. So at the leading and the subleading level, okay, this ambiguity is irrelevant. Okay. At the sub-subleading level, we have to keep in mind that this ambiguity is there, and you have to allow for this possibility. Yeah, the Riemann tensor of S mu nu has 2 derivatives, right? Which means 2 powers of soft momentum, because S mu nu is a soft graviton, right? So spatial derivative of S mu nu brings down powers of soft momentum. Right? So you have two powers of soft momentum. Okay. So the what you are missing, the ambiguity that you encounter by this procedure, okay, misses terms at sub-subleading order, okay, which you have to take into account separately. Is this clear?
Sorry, so you have the full action,
Yes.
but you choose to ignore some parts, and then it seems like you're introducing some ambiguity, and then I'm a bit confused.
Meaning
Full action, right? You have.
well, the point is I don't know this action. See that it is true that if I knew this action, I would have started doing Feynman diagram calculation with this, right? But I have to do without knowing the action.
But you need that action in order to derive the hard graviton Feynman diagram, which was in step 2.
Yes.
So you've already.
But we will not need it. We will see that we will not need it, right?
But you have the general theory.
Yeah. So the point is that of course we need that action, right? But we will see that the final result, the way it will be organized, the final result up to sub-subleading order will not need the knowledge of this action. Okay, we will start with the general form of the action and then proceed. Okay, are there questions?
So if you then only work with the full action, then there is no such ambiguity. Right?
No, there is no such ambiguity. Yeah. So if you work with the full action, if you knew the full action and if you do the calculation, there will be no such ambiguity. Right? And what is guaranteed is that the answer that you get by this procedure will agree with the result that you get from the full action up to subleading order. Right? At the sub-subleading order, the result may differ because we have not taken into account the terms involving the Riemann tensor.
So what you call as a soft graviton theorem is only in that general setting that you have, but you could prove soft graviton theorem in the full action.
Well, if we prove
Further away.
the point is, if we prove the subleading soft graviton theorem for this action, that proves automatically the subleading soft graviton theorem for the full action.
That's right.
Right? Yeah. At the subleading order, right, you can still try to prove subleading soft graviton theorem, the soft graviton theorem with this action, okay, by allowing for an explicit term which involves coupling of the Riemann tensor to the rest of the fields. See, we know that the whatever ambiguity there is, right, has to be in the form of coupling of a Riemann tensor. Right? So you can write down explicitly a most general term that couples a Riemann tensor to the rest and derive the subleading soft graviton theorem.
So I guess my question is, if you have the full action, is there some sense of the soft graviton theorem in the sub-leading order there for the full action?
Yes, there is, because that will be the same as what you get from here, because you will be allowing a general coupling, right, and you will derive the subleading soft graviton theorem here, right, which will hold for the full action, because for some choice of coefficient, right, this is the same as the full action result. Okay. So if you can prove subleading soft graviton theorem for arbitrary choice of coefficients here, right, then that will also imply that it holds for the full action.
So if you go one more order higher, then it will break down, I think.
Yeah, then it will break down at this or well, there also in general it will break down, because we will see that we can, in the full action itself, right, if we knew the full action, of course you can calculate the amplitude, right, then there's no thing about, so the theorem makes sense only if you can say something that is independent of what the original action was, right, and there will be similar ambiguities in the full action. In the full action also you can add terms involving Riemann tensor, right, and if that affects your amplitude, right, which cannot be absorbed into amplitude without the soft graviton, then that means that soft graviton theorem is breaking down. S mu nu is? No. S mu nu is the background, right? And we will be in fact working with linear order in S mu nu for the single soft graviton theorem, right? Because you only need coupling of one S mu nu, right? So S mu nu, what distinguishes S mu nu from H mu nu is that S mu nu has low momentum, right? It's slowly varying in space, right? Whereas H mu nu is fast varying field. Okay, but in terms of expansion, in fact, we will need powers of arbitrary powers of H mu nu, because we are not restricting how many external finite energy gravitons there will be, right? But you only need one power of S mu nu because you have only one soft graviton. No, between S mu nu and H mu nu, there is nothing, because we will be expanding in powers of both. For S matrix, right, we don't want to do anything for finite S mu nu or finite H mu nu. We have to expand out the action in powers of S mu nu as well as H mu nu.
In a specific theory, this sub-living contribution can become zero. That's what it is.
Yes, it can become 0. Yes.
If you have two different Lorentz invariant cases,
Yes.
will this thing make a difference in the
It will not make a difference because we know that by gauge that these two differ only by choice of gauge condition, right? So the individual Feynman diagrams of course will be different, but the final S matrix cannot differ. Right?
we are interested in some behavior with the AI invariant?
But still about a statement about the S matrices, right? And the S matrix is gauge invariant. Right? So if, as long as it's a relation between two sets of S matrices, it will not change if we choose a different gauge. Right? But certainly individual Feynman diagram contributions will be changing. Right? If we use a different Lorentz invariant gauge fixing condition.
If I choose, well, I make a choice that I do not have manifestly
Manifestly?
Lorentz, it's not manifestly Lorentz.
Okay, then I don't know what you mean by covariantizing it. If the gauge fixing condition is not manifestly Lorentz invariant, right? Because then you have broken Lorentz invariance, then the notion of covariantizing is not clear. Right? That's why you need a Lorentz invariant gauge fixing term. Okay, some choices. So we will take S mu nu. Of course, this is the standard form into epsilon mu nu to the I k dot x. Okay, because you are looking at a soft graviton carrying momentum case, so this is the wave function of the soft graviton. So this is the background about which you want to expand. Okay, and basically pick up linear terms in epsilon mu nu. Okay, and for the epsilon, I will choose the gauge condition epsilon mu mu equal to 0. Okay, and this together with the equations of motion will imply also k mu epsilon mu mu equal to 0. Okay, so this is the gauge condition on epsilon, the on-shell gauge condition on epsilon that we use. Yes, so the all indices raised and lowered by eta. All indices will be raised and lowered by eta. Pardon? K square is 0, yes. That's of course the on-shell condition. Okay, so this is the first. Second is that we will take all fields, all finite energy fields, see for any field in a theory of gravity, right, when you are doing an expansion, okay, take a gauge field, mu. Okay. You can either use mu as your fundamental field, okay, or you can multiply by an inverse hereby, okay, to take AA, where A is the tangent space index, as a fundamental field. Okay. We will take AA as a fundamental field. Okay, it's just a field definition. Instead of using mu as a basic variable, we use AA as a basic variable. And for all the fields, all the finite energy fields, including the metric, okay, including h mu nu. Okay. So h mu nu, okay, we convert to HAB, okay, by using the Theorem that we calculate from this metric. Okay. So let me write the yes. Yes, exactly. Because if the fields carry tangent space index, then its covariant derivatives will involve spin correction. Right?
If there is a covariant derivative, you write that covariant derivative index in terms of in that.
We will do that, yes. Yeah.
Then that will either total covariant derivative.
Yeah. So we'll see exactly how we do this, right? I'll do that in the next step. So let me just say the Theorem. Okay. So convention for Theorem. So convention. So E mu A will take to be delta mu A plus S mu A. Again, indices are less than lowered by eta. E A mu will be delta A mu minus S A mu. G mu nu, the inverse metric, will be eta mu nu minus 2S mu nu, etc. Okay. So basically what I am saying is that when you have an H mu nu, for example, okay, instead of taking H mu nu as your independent variable, okay, I take HAB, which is EA mu, EB nu times H mu nu as my independent variable. Okay. We contract with this, okay, to define new variables which only carry tangent space index. Well, this you can do even to subleading. When you take quadratic order, you have to decide on how to. This is to linear order, right? To when you want to go to quadratic order, which is needed for double soft theorem, for example, when you have 2 powers of S, you expand it out to second order. Okay? But nevertheless, you can always convert the curved indices to flat space index by contracting with these. This is the inverse. Yeah. Oh, because small e has mu down, a above, right? This is the inverse, which has mu above a. This is the curved space index, this is the tangent space index.
Yeah, the position of the indices, positions of the indices are enough to say.
Fine. So eventually we will not distinguish between e and mu. Okay. Doesn't matter. I mean, these are dummy indices anyway, right? So this is what it is. Okay. All indices a say mu is with respect to S mu nu is raised by eta, right? Is this clear? Kxa, yes, yes. Yeah, I think I have about 10 more minutes, right? Okay, I'll do one more step and then I'll stop. This step I'll repeat again tomorrow because it will be needed for tomorrow's. Yeah, so basically hopefully by the end of tomorrow's lecture I'll show why soft graviton theorem is true, that you can get a relation without knowing anything about the details of the action. Right? You can get a relation between the amplitude with soft graviton and the amplitude without soft graviton. Okay. and then I'll discuss the multiple soft theorems, right, when there are multiple soft gravitons. Okay. And if I have time, then at the end I'll discuss some explicit example, right, to test this soft graviton theorem. Okay, where you do independent Feynman diagram calculation or other calculations and verify that the soft graviton theorems are really true.
Is there a theorem just like we have the Lewis theorem where it's a charge, so if I have low scattering, say constant angle to mass or spin associated with the magnetic moment, these are the low energy theorems which are to all orders in strong interaction.
Yeah, so these will be analogous to that.
And the corresponding theorems here.
Yeah, so the leading soft theorem, for example, will tell us that the coupling of the graviton to leading order is through the mass, right? The subleading one, okay, which is a new one, which was discussed only in the last few years, is that the coupling of the graviton is through the spin, the say subleading order, and then there are further corrections which are non-universal, okay, where there is no universal result like yeah, exactly, okay. But for example, for the for QED, okay, even at the subleading order, the universality breaks down, okay, because the magnetic moment is not universal, right? Different particles can have different magnetic moment. But for graviton, you will see that the subleading one is universal. Okay, it's only at the sub-subleading order that it starts becoming non-universal. Okay, so now covariantization. So suppose you have a field phi alpha, okay, where alpha is some tangent space index. So if the original flat space action had some del A1 to del AN of phi alpha, okay, what will you do to covariantize it? You will replace this by EA1 mu1 pardon, d mu1, is this okay? I use? Oh, these alpha, okay, these are Greek alphabet but different kind of Greek alphabet. So these are tangent space index. Okay. So see, A, B are vector indices, right? These alphas can be spinor index, vector index, I mean anything, right? Tensor index. So that's why I am using a different kind of symbol. Yeah. So for this d mu's, I have to use covariant, the standard covariant derivative. So for example, if you have d mu phi alpha, this will be del mu phi alpha plus half omega mu AB JAB. This is the spin operator. Okay, that's the standard definition. If, for example, you have d mu d nu phi alpha, then you will get first is del mu plus, let me write in the more abstract notation, omega mu AB JAB, okay, as a matrix operator, but then plus you will also have a Christoffel symbol. Okay, let me write it as two different terms. So there will be one term like this. But then there will be another term which is Is clear? So this is the usual covariant derivatives acting on a field carrying tangent space index. Okay. But once you have a d nu acting on this, okay, the second covariant derivative will also have a Christoffel symbol, because now this object has a curved space index, right, besides the flat space index alpha. Okay. So you have this part is sensitive to the fact that this is curved space index, the phi alpha, but then there is a Christoffel symbol, okay, which takes care of the fact that there is also a curved space index nu over here. Okay. And then if you have multiple d's, you will have a similar structure there. So this is a procedure that you have to do to covariantize. Okay. This looks complicated because there can be arbitrary number of d's, okay, but we will see that in the next lecture that there is a simple way to convert this into a prescription in the momentum space. Okay. So this covariantization procedure will take a simple form when you work right in the momentum space. Okay, and that's what we will do to write down the coupling of the soft graviton to the rest of the fields. Okay, so this point I will discuss in next time in more detail. Okay, so I think I will stop here.